Thank you very much. So this is joint work with my colleague Qiaozhu Mei and our students Jingyi Qiu, as well as our former student Teng Ye, who's an assistant professor from Minnesota. So I'm going to start with two challenges. The first challenge is after ChatGPT was released, we observe a decline of content generation in online knowledge communities. So this figure is from Birch et al. And the one on the left is looking at content generation in Stack Overflow. So this is an online community for programmers it's an online question answering community. So programmers can ask and answer questions with each other. And so the exit was primarily new users. And we see a steady decline because people now turn to ChatGPT and other LLMs for their programming questions, which is concerning because it's a long-run online community for this space. On the right-hand side, you see the traffic on Reddit. And this is a subreddit also for programmers, so that's another Q&A. And the reason that you don't see a decline on Reddit, the speculation in this article was that because Reddit also have other type of social support and social interactions, whereas Stack Overflow has a fairly strict rule of on-topic technical discussions. So when that technical discussion is gone, people left the platform. So that's the first challenge, which is these contents are used as training data for these language models. And so when humans stop contributing and generating these comments, what's going to happen to the progress of AI and lots of other questions. The second, which seems unrelated, is increased political polarization. So we're going to actually put these two challenges together. So what you see here is the American National Election Studies. This is one of the questions that was asked repeatedly. And this figure is from Druckmann-Levy's 2022 study. So this is a thermometer question. On the vertical axis, okay, here, can you see? I guess you can't see. Okay, I'm just going to describe it. On the vertical axis, you see a temperature scale from 0 to 100. And on the horizontal axis is from 1980 to 2020. And the question was, how do you feel, how warm do you feel about the Democrats and the Republicans? And the green dotted line, so if it's above 50, you feel warm about a particular party. If it's below 50, you feel cold. And so the temperature reflects your attitude towards a political party. So if you look at the green dotted line on top, people's attitude towards in-parties has been fairly steady over the last 40-some years, and is around 75. The blue dotted line reflects people's attitude towards the out party. So if you're a Democrat, this is how you feel about Republicans over time, and vice versa. And that has been decreasing over time. The difference is the orange line, which political scientists use to characterize affective polarization. So that has been rising steadily over time. And if you read news, we don't really need to elaborate on this point, which is we're in a world where we disagree on a lot of things. In addition, we also dislike our groups. So an opportunity is we're going to put these two challenges together and propose a research project, which is to get people with different political views to co-edit Wikipedia articles together. So Wikipedia, as you know, is among the top 10 most visited sites in the world. And there are 64 million articles in more than 300 languages, and it's developing, still going up. And each month there are about 1.8 billion unique devices accessing Wikipedia articles. It is also among a consistent training data source for the large language models. So in the Wikipedia environment, there are 5 pillars for editors to observe when they edit Wikipedia articles. And the most important one is neutral point of view, that all views should be reflected and according to their importance. There are many controversial articles on Wikipedia, and that often reflect the political polarization in the society. So one can identify controversial articles by looking at the edit history to look at how many reversions this article has. You can also look at talk pages where editors discuss and argue with each other about whether to incorporate a particular point of view. And I'm also going to mention the effect of LLMs. There wasn't an immediate decline of page views on Wikipedia after LLM was first released. So in 2023 and 24, we don't see a decline, but in 2025, the new estimate is that there's the number of human page views are about 8% lower month to month compared to 2024. So what we're going to this project, what we're going to do is to look at controversial topics on Wikipedia, such as immigration. And we're going to recruit editors and put them into a team. They could either collaborate with a human editor with a different prior belief on a politically sensitive topic when producing Wikipedia content. We're just going to call them disagreeing editor. And they're randomized into collaborating with either a human or a large language model on the editing processes. So from now, I'm going to use the running example of immigration to illustrate. So we asked 3 questions. One is, how does collaboration with a disagreeing LLM versus a disagreeing human editor affect the quality, neutrality, and credibility of the final paragraphs this team contribute to Wikipedia? And how does each collaboration experience affect, the humans' beliefs about, immigration-related questions and their attitude towards immigration and immigrants? And we also want to look at what is the participants' willingness to collaborate again with a human versus LLM editor. Okay, thank you. So the conceptual setup is we're going to form teams with disagreeing editors. And how do we do that? We start with a pre-survey. So this has been piloted. We start with a pre-survey to elicit their general attitude on immigration and position on the economic effects of immigration. For example, on local labor market, and we incentivize them to play a game to elicit their contribution decisions to different campaigns. The team composition is, we're going to summarize research articles on immigration and their effect on the local economy. One from a slightly pro, the other one from a slightly con aspect. They're going to read the research summaries and then individually write up a Wikipedia-style paragraph summarizing the evidence to contribute to an existing Wikipedia article on the topic. And then the main part is the collaboration with a disagreeing teammate, which could be another human editor or LLM. They can view their teammates' summaries, discuss and co-edit a final synthesis of the paragraph. Then we elicit their posterior beliefs and ask them to play an incentivized game to elicit their attitude towards immigration. And so here are the main hypotheses. So the final Wikipedia-style paragraph in the LLM condition, we anticipate that it will be rated as at least as high in overall quality and neutral, balancedness as those in the human condition. The second one is on updating, and we anticipate that the magnitude of updating will be greater or equal in the LLM condition compared to the human condition. So this is updating from a more extreme perspective towards a more neutral perspective. And the third one is collaboration experience. We anticipate that the willingness to collaborate again in the LLM condition will be at least comparable to the human condition. And so we ran some pilots, and we had 20 matched participants. So in terms of paragraph preference, whether you want to submit your own paragraph, which is more biased, versus submit a merged paragraph, 65% chose the merged paragraph, and about a third chose their own. And on the willingness, there are also some other outcomes based on 20 matched participants. So we haven't done the human LLM condition for this experiment design. In a previous iteration, we find that human editors had a better experience with LLMs compared to with another humans. But there we actually label the humans as Republicans versus Democrats. And the conversations seems to be much more polite when they talk with LLMs. Let me just wrap up on the expected implications. So we anticipate to come up with a set of strategies to reduce polarization in online platforms, and also a set of guidelines for effective human-AI collaboration. So that's I think I'm out of time. Yeah, okay, thank you.
Thanks for the really interesting talk. It looks like it'll be a fascinating study. Couple of questions here. Several questions. So might it also be relevant or interesting in this context to compare agreeing pairs of human-human and human-AI as opposed to only disagreeing pairs?
Yes. We could add those conditions, and what tend to happen is if you have, so actually there have been a fair amount of research looking at people who, have similar priors, and after collaboration, they actually move to more extreme conditions. So that's something that we know. Yeah.
Interesting.
Yeah.
Still okay? Okay. So there's a question about how does the generally agreeable tone of mini LLMs play into this? I guess the LLMs are trained to be polite, et cetera, et cetera.
We post-train them to adopt a position.
Interesting.
Yeah.
Okay, so they're not necessarily very agreeable when they are interacting with the...
Oh, so for the pilot study that we have conducted, they are, the LLMs have been consistently polite in interacting with humans, whereas human editors, when, with labels, when they're labeled as Democrats or Republicans, tend to go into a more argumentative mode, and they're not always polite towards each other. So this is why we take the labels off, and we just tell the participants that this is someone who has a different view from you, in the pre-survey. So without labeling, without giving the participants a partisan label.
Interesting. I'm not sure. Do we have time for one more question, or should we move on? One more. Okay. So here's I think an interesting question. So what is the process that you use for discouraging sycophancy in the specific LLMs that you're using? Prevent them from being...
Discouraging, I'm sorry, what?
From making them less sycophantic, less... Do you know what I mean?
Yeah.
I'm not sure what's a synonym for sycophancy.
I guess too
eager to please and to agree and so on.
So we prompt the LLMs to have a neutral point of view, to have a polite tone. So there's a set of instructions for the LLMs.
I see.
Yeah.
Interesting. So it sounds like there's quite a number of questions in the group that are more related to the methodological details. So I encourage you, if you're interested in following up, you'll be around for a bit. So perhaps you can seek her out for the break. So thank you very much. Let's thank our speaker again.
Thank you. Thank you very much.
We speak to training data integration, where now we allow the ABM to really get into the massive exploration of the data and parameter combinations, just to be able to cover the full epidemiological space, and at the same time looking at the network architecture, looking at what goes in, what are the hidden layers, what's the activation function, and at the same time trying to look at the prediction targets like the number of cases, what's the peak time, what's the magnitude at peak, how many were hospitalized, what were the reported cases of mortality, of death, and also how long did it take, of course taking into consideration also the regularization. Then we had to train the neural network, and of course the use case here was Kenya, not for any particular reason, but I come from Kenya, and so it was reliable to speak to a data that I closely relate to. Yes. And so this is what the hybrid looks like. We have the ABM and its complexity and the small details that we are trying to put together into a puzzle. And then we have the neural network that fastens the computation process. And then when we train all this, we are able to speak to solving a specific problem of speed, which then would inform policy and also other interventions, but trying to our very best to validate and deploy our data. And so, while I speak to the small details, in our use case, we were able to control the environment in terms of the household. So the household was our primary environment, and our assumption here was you come from a house and go back to the same household. So transmission could happen from outside or from within, going in, from in going out, or from out coming into the house, into the household. So the household was considered as a primary environment, and then because we were we ensured we simulated a complete demography, then schools also were environment that was of interest to us, and also workplaces. And that's the match we could do because of the computational requirements. But if we were to adopt a simulator, then it would be interesting to also look at some of the sporadic contacts in public spaces, like market, transport venues, and all that we did not necessarily capture. So we had 3 environments that were that were of interest to us. And we were able to calibrate this model to fit the Ministry of Health data. And so it successfully reproduced the observed case trajectories during the first wave. And it did this really fast. And so we were able to see more or less the same kind of observations of 45 days with a 3-day error and nearly 93% accuracy. At the peak time was around 2,200 cases per day. And then the overall trajectory was at an R-squared of 0.81, which somehow indicates a good fit, but also allowing to the other specifics that were not fitted into our parameter. And then the spatial heterogeneity was also important to us because we realized that the urban centers, so the movement, specifically for Kenya, we have a lot of people staying in the urban areas, and so it's more densely populated. In the urban areas, it's densely populated compared to the rural areas, and that was able to feature out explicitly. And then, of course, I've spoken to the age-stratified outcomes. We saw the working age, the primary transmission drivers. The elderly were the highest hospitalized, and then children had low disease severity, which was driven by adult-to-children transmission. The model itself, I would say it was a high-fidelity surrogate performance, but I'll say that carefully, because looking at some of the parameters that we were able to fit into our model, we may have missed to take into consideration other primary parameters, but it did try to fit nearly the same as how we would have used the traditional model by itself, except it was much faster. And so we noticed that, I think I've already spoken to this, and I'm saying that the optimizer evaluated thousands of parameter combinations by calling fast neural network instead of the slow agent-based model simulation. And the model calibrated to reproduce the observed COVID-19 epidemic trajectory in Kenya during the first wave. That was between March and August of 2020. And so, I have already spoken to the practical implication around time reduction, but also just to appreciate that the data quality dependencies. The neural network accuracy depends on the agent-based model training, data quality and diversity. And so if you do not define your agent-based model accurately, then that means the neural network will also be affected. And of course, the extrapolation limitation is also something to take into considerations. So novel scenarios outside training space may show degraded accuracy. And what I mean by this is, for example, I am using the agent-based model that fits into the demography of Kenya. If I try to adopt the same in Uganda, Tanzania, which are the immediate neighbors of Kenya, and from a spatial context, you'd assume that the disease spread would want to appear more or less the same. But if the demographics are different, then the accuracy will definitely be affected. And so we are looking at the interpretability trade-off, the quality assurance, but also maintaining the requirements that are of interest to us. Policy-wise, this fastening the process helps with the decision support for rapid response. And I think we'll all agree to the fact that after COVID-19, it would be great to, while we do not know which pandemics would come, the thing is, if we have new pandemics, then rapid response would be something that we want. The decision support for rapid response would be primary for anybody, whether you're a policymaker or not. And then, of course, uncertainty quantification and risk assessment would be something that we do not want to overlook. Speaking again to the small things that matter to me, I did not exhaust everything around this kind of hybrid model. We still have like 3 other larger areas of research that would be for future research, I would say, or would be of benefit to advance what we have already started on. One of them will be the multi-pathogen integration, so looking beyond COVID and speaking to other infections, vector-borne infections maybe, influenza, RV, and any other, just to see how best this kind of model can be able to emulate the same. And then speaking to the real-time adaptive learning and the advanced machine learning architectures, but also taking into consideration the computational requirements. That's the end of my story. Thank you.
Stimulating. So there's quite a few questions here. First of all, let's see. Would it be possible to interrogate the model pipeline, I suppose the model and the inference procedures and so on, to identify where more data would be most useful, or what kinds of data would be most useful to improve the practical utility, I suppose, of this approach?
Yeah, it should be possible. I mean, it would be important to evaluate the model pipeline, and we tried to see which kind of data would actually be useful. And so, of course, we were keen to understand the agent-agent interaction, but at the same time, picking on specific environments that we were certain were critical for us to be able to map. And that's why I spoke to the household as a primary environment. The schools where the children were studying were also a primary environment, because during lockdown, then it means there were less interactions around those spaces and the working spaces. And so, okay, that was our high-level thinking. But of course, as you go deeper or you go granular, even as you assess the kind of model and you check within your pipeline what would be essential, it would vary from one context to another. But it would be important, yes. Yeah.
I see. Okay, so here's a question. Could you speak to what are the practical considerations for implementing AI-driven public health interventions and analysis in Kenya specifically? And what would it take for large-scale rollout of such systems to be able to assess epidemic risk?
Sorry, I didn't get that.
So I guess they're asking about what are the prospects for rolling out these kinds of AI-assisted epidemic management approaches in Kenya specifically?
I would say it's an opportunity that we need to really explore, because it would really work for us in the sense of, or maybe, okay, for Kenya, for example, we also had cases of unreported, like data was incomplete.
Yes.
And so when you think about integrating these kind of models, you can work with sparse data or underreported cases to be able to project and see exactly. depending on what is your priority, is it the intervention that you want to really assess and see what would be the primary intervention? If it is the vaccination, then what age groups do you want to vaccinate? For example, you would assume you need sufficient data around the different age groups, but sometimes it may not be the case for Kenya because of the underreporting or maybe missed cases. But if you integrate the agent-based models, looking at the scenarios like based on the simulation, and then overlaying the calibrated data much as they're sparse, it can give you the indications on whether you want to integrate interventions. So thinking of lockdown and maybe the vaccination, or maybe enhancing other non-pharmaceutical interventions like distancing and also mask, maybe for also speaking to the period that you want to enhance different interventions. I would look at it as so, but yes, there is a lot of opportunity of trying to see how best you can integrate AI into this kind of epidemiological context to see how best you can be able to address specific epidemics. Yeah.
Very good. So here's a question, sort of, I guess, asking for your experience during the COVID pandemic. So when time is of the essence, how can we verify the computational work and the statistical work, the policy evaluation work that we're doing, while still making decisions based on AI models? Maybe I read too much into that question. So just to read it, when time is of the essence, how can we verify the work while still making decisions based on AI models? And it goes on to say, lives were at stake in COVID, but if the models showed the wrong info, perhaps we would make a bad mistake. Any thoughts on that subject?
I like the fact that we agree to some extent that these models sometimes they're wrong. Well, in statistics, we don't say they're wrong. We say we have assumptions. So for example, you've had for linear models, we assume the errors of prediction are independent of each other, right? We're just trying to play safe instead of saying the model is wrong, yeah? But this is what you're saying. If I'm designing my agent-based simulator, the amount of information that goes in there should be as accurate as possible. Because now when the AI comes in to fasten the whole process, it relies on the training of the information that is provided from the agent-based models. And so if that information is not accurate, then of course you'd expect inaccuracy at the tail end of where we are speaking to what needs to be done rapidly and all that. And so it's entirely dependent on how much information can be captured, how fast that information can be captured, which again, I would say in developing countries, it's yet another challenge because when it comes to public health data, the access and then the completeness is yet another problem. So the model might work well where there is rich data, rich, correct data, and it might fail to perform where the data is either incomplete or incorrect. Again, that's just the assumption, not a wrong model.
Fair enough, fair enough. Okay, so one more question, and this one is a bit more speculative, let's say. So will we get to the point where AI can predict the next pandemic before it becomes a pandemic?
For me, I would worry less about predicting the next pandemic, but I would worry more about how fast or how quick we respond to the next pandemic. Because I think the response is the most practical. The forecasting of the next pandemic, maybe it can. I can't speak to the accuracy. Just maybe, yeah.
Fair enough.
Hopefully, it should.
Yeah. Okay. Well, let's thank our speaker one more time.
My name is Milo Parrott. I'm a graduate student instructor at the University of Michigan College of Engineering. I've been affiliated with the Department of Nuclear Engineering for the past 5 years. And most of this research has been in conjunction with the fusion energy startup company Helion Energy. So the example I'll be giving you will be one of their fusion machines. So as has been touched on in many of these talks before, the current surge in AI, machine learning, and cloud computing has caused a lot of new data centers to pop up. And this has caused an unprecedented spike in the amount of energy consumed by the US grid. What you may have heard before is that nuclear fusion energy has been proposed as a solution to this energy spike. And although the technology is somewhat far away, in the near-ish future, say the next 10 years, it could be the clean and cheap solution that the US is so desperately in need of with all of these new data centers and electricity demand. But what you may not know, what you may not know is that fusion energy itself can actually benefit from machine learning and AI. And that's something I'm going to touch on today in my talk. So just quickly, what is fusion energy? So fusion energy is very similar to nuclear fission, which has been powering some of the US grid for the past 50 years. Although nuclear fusion would be a lot cleaner, it does require a lot more challenging technical constraints. A lot of concepts have been proposed to deal with these technical constraints. The one from Helion Energy is shown up on the board here, and that is fusing two balls of plasmas using inductive magnetic coils. Got a video for you. So what you can see here is a ball of gas being injected into a cylindrical container and then being accelerated towards an identical ball of gas or ring of plasma. And once you reach high enough collision velocities as well as ion temperatures within that ball, what happens is that some of these particles actually fuse and become larger particles. Well, they release a very small amount of their mass as pure energy, and this can be recaptured using Helion's machine here. The issue with designing machines like this, which are far from perfect at the moment, is that each shot or experiment is rather expensive. They take a lot of time and energy and money to set up. So, like all other companies nowadays, what Helion does is they use a code to simulate the machine. The code that Helion uses is called Cygnus. For those familiar with plasma physics, it is a Magnetohydrodynamic code. Essentially, it is a cheap way of simulating what happens inside of Helion's machines so that they can conduct informed experiments instead of just firing at random or based on physical theory, which does still play a part, but simulation is definitely a faster and cheaper way to make predictions like these. So what you can see here on the board is a simulation output from the Cygnus code. And essentially, this is the ion temperature within that plasma ball I showed earlier in the top right section of the machine there. And because we have a lot of symmetries in this machine, this amount of data or this spatial profile is significant enough to provide information that Helion can use to make informed designs. However, simulations can still be expensive. Some simulations can take up to weeks, months, years. The Cygnus simulations in specific take anywhere from 1 to 8 hours. So my research vision was to build a neural network to act as a surrogate model for these simulations. The structure is fairly simple. For predicting 3D outputs, we use a convolutional U-net. And for 1D outputs, we use a convolutional spatial net. And the inputs or experimental parameters that we're optimizing are the voltages or strengths at which we fire those magnetic coils that accelerates the plasma, as well as the timing at which we fire these coils. And by varying these two parameters, we can look at different outputs that coincide with high fusion burn, which is something that Helion is trying to achieve. And a good example of these would be, here on the next page, the ion temperature, which I mentioned earlier, which you can see is predicted very well by the neural network, and the electron temperature, which is also predicted fairly well by the neural network. So these GIFs, visually at least, prove that the SIGNet, which is what the surrogate net is called, is an effective way of predicting what a Cygnus simulation will do, or predicting its performance. They do make working inferences. Oh yeah, and I'm sorry for the lack of units. The units are EV or electron volts for anybody familiar. So here you can see some quantified metrics rather than pretty GIFs that show that the Cygnus neural network or CygNet performs somewhat accurately. The top right plot or top left plot can be a little confusing. Essentially what you're looking at in blue there is the mean squared error between a true and inferred output. And the orange distribution is the comparison of mean squared error between all outputs. So this sort of serves as a baseline to show how different all the simulations are from each other, and then how accurately they're predicted compared to that, which is in the blue. And you will note that there are a few outliers. If we have enough time, I'll get into that. Another very important metric that we discovered with Cygnus was the speed up factor. So the CygNet was able to make predictions in about 1/10 of a second, where these simulations take anywhere from an hour to multiple hours. So that's a very significant speed up factor. And with sufficient accuracy, the CygNet neural network gives Helion the capability to make these predictions very rapidly, much more rapidly than they could before with Cygnus. Of course, there are a few issues. Like, you do have to train this on simulations, meaning you do have to conduct simulations to train the CygNet on, which is an upfront cost. But once the tool is trained, it can be used many, many times very fast and very rapidly. In addition, we had to reduce some of the spatial and temporal resolution, but that's just for data issues. So now that we have this neural network, these trained neural network weights, what can we actually do with those? Well, for one, of course, we can make rapid predictions about very basic ideas and see how they would play out. But with the trained neural network, we also found we could build a very, very, very rapid optimization algorithm that outperformed a lot of the basic optimization algorithms that were devised using just the Cygnus simulation. Meaning, with the trained neural network weights, we could optimize for desired quantities within hours instead of weeks or months. And so you can see here that the ion temperature on the top there and the axial velocity, which basically designates how fast that ball of plasma flies towards a collision, both of which are very important parameters for high fusion reaction, were optimized quite successfully, and they outperformed just sampling all of the training data it took to create the CygNet, which was very significant. We also tried some normal optimization algorithms using just the CygNet as the predictor of loss, and the neural network version outperformed significantly. So now that we have this trained neural network and all these capabilities, what is really the vision? So my idea in implementing this in Helion's infrastructure is taking this sort of week per idea evaluation down to a minutes per idea evaluation. So experiments are expensive, like I mentioned earlier. They can cost anywhere from $1 to $1 million in terms of fusion energy. In some regimes, they can cost even more money. They are, of course, very accurate, which is nice, but they're too expensive to be practical to test every single idea that one has about a conceptual idea for producing fusion energy. So the next layer up, which would be Cygnus in this situation, is simulation. And that can take anywhere from half an hour to many, many, many days. And they are generally pretty accurate within certain regimes, but they still are expensive in cost and in cost and time. And that is why we designed the CygNet neural net surrogate, which is not a replacement for Cygnus, but more of a quick tool to rapidly test ideas. So we're going from maybe weeks per idea down to minutes per idea. Let's see. However, the CygNet is not perfect, obviously. With neural networks, you do run into many issues and many sort of constraints you have to be aware of when using them responsibly. The first of which we ran into with CygNet was regime coverage. So The model, like most neural nets, has a lot more trouble extrapolating than it does interpolating. So this is an issue because once you've trained a neural network and spent all this time and money creating training pairs, you can't really do anything outside of that regime. And the second benefit is that when you use this sort of like pulsed collision configuration, you can recapture the energy that comes out of it electrically and like inductively. Yeah, instead of turning neutrons into heat and heating water, which is typical, even in most nuclear fusion reactors. Very tried and true method with energy. So, believe I was on regime coverage. Moving on to the second issue with the SIGNet architecture was the error propagation that we saw across this sort of stack up, going from experiment to simulation, and then back up to the SIGNet structure. So when you're using a surrogate of a simulation is essentially already a surrogate of reality. So you're really 2 layers removed. And this can be an issue because errors can propagate and bound in this situation. And there are fixes to this, but it's something you have to be very aware of when using a pipeline like this. The third issue is very simple. It's really just compute operations. The data outputs for plasma physics simulations and other simulations are very heavy, right? So you need somewhere to store them. You need to store a lot of them overhead as you train a neural network, and this is really just mitigated by careful data operations and buying larger computers. So how do we deal with all these? Well, for regime coverage, the answer is pretty simple. You just have to train your training data set or generate your training data set on a very well and efficiently chosen regime of physics. Say, sit down, maybe talk with some of the physicists on your research team or other scientists that can provide you with direction that you need to make sure that you're training in the most effective way. You want to get the most use out of each data point because they're so expensive. For error propagation, this is pretty simple. What you want to do is you want to make sure you close the loop. And by close the loop, what I mean is every time you reach an optima with your neural net optimizer, in my case, the SIGNet optimizer, you should always check that against simulation. If simulation proves it's valid, only then do you move on to experiment. Neural networks it's very hard to prove that they're accurate because of their black box nature, especially in cases with weird physics and when you're trying to optimize towards maxima, which is generally where the physics of simulators are broken. So, like I said, always close the loop. It's very important. Data and compute operations, like I said, the fix is very simple. You choose very, very carefully what you want to use as your training data and make sure you store your data in the most effective format. Sure, most of you are familiar with this. So how do I envision this as being implemented within a Helion structure? So the structure in general I've already touched upon, but I'd like to just go over the loop one more time. We have the neural network. It's trained on a very specifically selected subset of training data. Then the optimized inputs from the neural network are passed on to the simulation, with the simulation confirming the neural network or rejecting the outputs of the neural network and sending them back to the neural network for using the next best optimized quantities, or next best optimized inputs, excuse me. Then we can move on to the experimental machine. And if that works, fantastic. We can continue to optimize and going through this cycle. And if it doesn't, we go back. So I'll just briefly run through these because I know we're short on time, but my vision in the future, I quickly want to decide what targets would be optimal to optimize upon. So far I have, like I mentioned, ion temperature and propagation velocity. This is really just a lot of physics deliberation that will help me decide what sort of training set I want to look at. From there, I already have proven that the SIGNet works and can be trained and is fairly accurate. And then I'm going to, once I have some results using the SIGNet on the optimization targets, or once I've optimized for these targets, I'll present my findings, and then from there, we move on to some more complicated geometry and integrate directly into Helion's workflow. So this timeline doesn't, or this template doesn't work just for Helion. It works for many, many, many different pipelines. Essentially anywhere where you can create a reasonable amount of data and you would like to make a surrogate for a simulation code. And I think for the sake of time, we'll just to leave everybody with one last piece of advice. So once you've created a pipeline like this, it's very easy to say, okay, yeah, this works. We've got great metrics on the neural network, but it is vital to close the loop and go back from your neural network to your simulation and back to your experiment. And I believe that's everything. Thank you all so much for sticking around. Sorry about the technical difficulties.
No, I think we're supposed to be the ones to apologize for the technical difficulties. Thanks for the great talk and for putting up with those with aplomb. So a few questions have popped up here. So I guess a fairly technical question. Is it possible or necessary to prove the correctness of the neural network emulator in this context?
Yes, you can prove the correctness as it makes specific predictions, but it's impossible to prove its correctness in its entirety because no neural network, of course, is capable of predicting everything. You have to stick within a specific regime. And to prove the exact correctness in a physical experiment, I mean, that takes days to set up. So to prove an entire regime at a sufficient interpolation size would be nearly impossible.
So this comes back to your question about closing the, or your point about closing the loop.
Yes,
right.
Absolutely. I think to prove the correctness, you do have to close the loop.
Right, got it. So, and then here's a question that's, I guess, more about the current state of fusion technology. So it says, in the past days, Verrah Atomics claims to have reached criticality. Have you had a chance to review their claims, and do you think they are credible?
I actually have not had the chance to look over that. I will certainly look it up after this. I am curious. What was the name?
Verrah Atomics.
And this is a fusion company? Interesting, okay. A lot of claims come through in the field of fusion energy. I don't think many of them are generally true. I cannot speak to this one specifically, but yeah, I'll have to look into that. Thank you.
Okay, so are there any further questions from the group? Okay, well, let's thank our speaker one last time, and thanks for the great talk.